Okay. So we'll just go through the presentations today. We'll just go through them in order. We had one person switch to Saturday, so we have the gap, but so we'll just probably try to move things up so we're get done and make sure we're done before the 10 o'clock final exam time in case someone has a 10 o'clock final. So right. As always, I don't mind you ignoring me when I'm up there, but when we have students up there, we want to give them our full attention. So except Nick, Nick's not actually the class. Give them a what, Nick? We can give students their full attention here. So
Okay. Good to go.
yeah, there you go.
Okay. Hey guys, I'm Taku, and today I'm going to be presenting about language called Mojo. And I coded the perfect middle ground. And it's gonna make sense as we go through the slides. So why did I choose this? So Mojo is the perfect middle ground, as I said, because as I grew up, I learned to program using Python just because Python was very easy. Since when I was in high school, the first programming classes that we took, we usually use Python just because of how easy it is. So when I was doing my research, I wanted to find something that gives me the simplicity that Python has, but that can also carry out the heavy computational programs that Python might not be able to do as fast as other programs like C++. So Mojo, that's when Mojo comes in, because Mojo gives the traditional trade-off. it gives the performance that you could expect from the likes of C++, but it gives the simplicity that Python has. As I mentioned that, Python might be slow on some heavy computational tasks, but Mojo gives you what Python can give you in terms of, learning how to code and its simplicity, but it also gives you the performance side of it. And this language was introduced 2 years ago by a company called Modular. And it was introduced for this specific reason because the company called Modular, it focuses on promoting AI applications and programming, or it helps programmers advance their careers in collaboration with AI. So it's sort of like this new AI phase, and Modular is a key part of it, but because it combines AI with programmers. And the key features that I've seen in Mojo, they include the syntax that is very similar to Python, and it is beginner friendly. As I said, that I wanted something that, relates with myself because I learned, programming using a very simple language like Python. So it's beginner friendly. You can use it in high school. You can use it. It can be used by any person who is trying to kickstart a career in programming. And it has also features that include static typing, and compile time optimizations. And there is a code that I got from ChatGPT that shows an example of these features that Mojo has. And the performance and MLIR integration. So the module, it performs advanced optimizations across hardware types, and it delivers the speed that you'd expect from C++ and Rust level. Rust is another, not really an emerging language, but it was introduced, if I'm not mistaken, in 2009, and it is the kind of speed that you would want in heavy computational tasks. And this is what you can get from Mojo as well. And then seamless integration with Python libraries. So if you are someone who has been working on a project using Mojo, using Python, and you now want to change it to Mojo for any reasons, it's very easy to do that because it has a seamless integration with Python. So you don't have to change your code base that much when we're switching from Python to Mojo on a specific project. So that means you can reuse existing code, and that's an example of a code imported from Python. Memory management and parallelism. So these are the features that I researched and found that it has a hybrid memory model. It has automatic reference counting and manual memory control. It has an offline type system which ensures safety, and this was inspired by Rust. And it has a built-in concurrency and parallelism support. So to me, when I say it's a perfect middle ground, I'm looking at three programming languages: Rust, Python, and C++. So that's why we can see that even the offline type system is also tempted to be inspired by Rust as well. And real world impact and final thoughts. So because it's supposed to be an open source and community driven. I think it's very, it's good for, as I say, that if you can use it in high school for students who are still learning to code, it's very important that it's open source because anybody who wants to, start a project can use it. And I also think because of the fact that it's very easy to use, that means, it's easily accessible to students, and it also easily accessible for startups, of course, because of, the kicks, the surge in startups recently because of AI. So that would be very key too, in my opinion. And as I say that, it combines the best of Rust, C++ too, which is not listed in that, Go, for simplicity, and Python for usability. Mojo is a platform for democratizing high performance software development. So I think this quote just, summarizes everything that my presentation is focused on. It makes, high performance software development simple, unlike we would have, in other languages. And these are my references. And thank you.
Or do simple trusted or something. It's not that popular or, new language. So
Yeah. So, as I say that, I just wanted to, I didn't know anything about it before, but for this project, I wanted to find something, a code that is simple to use. Because for me, I learned to program using Python. So I wanted something that is kind of similar to Python, which is very new, but which is also some other, better features, or which is better capabilities that you might not see in Python as well. So that's when I saw Mojo, and I saw that it was introduced in 2023. Then I was like, it's the perfect fit for the presentation because we had to do an imaging or a new language. Yeah.
can it run Python code? Because that's static. You said at some point in one of the slides that it's compatible with like Python libraries. But but it has static. The example you showed had static type. You had to declare the type of each variable, right? So if you have some Python code, you have to tweak it a little bit.
I think so. I think you have to tweak it a little bit. And when I say a little bit, it's definitely just a few tweaks, because it actually says that you can be working on a project and you don't have to change your code base. You can work with your existing code. And because the syntax of Mojo is very similar to that of Python. So I assume that the changes that you have to make are very slight changes. I think that in one of my classes, if I'm not mistaken, that was software design, where we had a language where we had to just tweak a little things from that language into C sharp, if I'm not mistaken. So I think that's a similar kind of thing where you just have to change it a little bit because the syntax is very similar.
I think, because of Python's performance issues, I think a lot of the Python libraries, the big libraries, are actually written in C or are not written in Python.
Exactly.
So like NumPy, TensorFlow.
Yep.
And that's because when you do like machine learning stuff.
Yeah.
What slows it down usually is that you have some library reading in an image or a big array.
Yeah.
And then it's in Python, and then and then you eventually are passing it to NumPy or to like TensorFlow.
Yeah.
And then it's fast again, but just that bridge.
Exactly.
Yeah, it slows down. It kind of gets into Python native stuff.
Exactly, because I saw something when I was researching about this, which say that usually when programmers are programming with a Python code, usually they end up switching from Python to different languages in order to program some operations. So in order to limit that back and forth, if you're able to use Mojo for that makes it very much easier. And I also have a real life example when I was applying for a software engineering role at Goldman, and I talked to this guy who works at Goldman Sachs in the engineering department, and he was like, "So, what languages do you know in programming?" I think I was a freshman, if I'm not mistaken, and I was like, "I've only used Python." And he was like, "No, you cannot use Python for software engineering. You have to know Java and all those all kinds of other programming languages." Just because of that, that's why it's a more your democratized software development.
Right.
Yeah.
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 All right.
All right. Thank you.
That's nope.
So I'm Allie, and today I'll be presenting my research on the theoretical limits of computation, and their impact on artificial intelligence and machine learning, but also how it reflects deep constraints on human reasoning itself. This topic helps us understand the boundaries of what machines, and by extension, we can know and solve. So theoretical computation studies the mathematical foundations of what computers can and cannot do. Concepts like the halting problem and undecidability highlight that some problems are inherently unsolvable by any algorithm. Understanding these limits is crucial, especially as we build increasingly complex AI systems that interact with unpredictable real-world environments, which I'll discuss later. So Alan Turing introduced the halting problem, showing that no algorithm can determine in all cases whether another program will stop or run forever. That led to us or discovering undecidability, the idea that some questions simply cannot be answered algorithmically. And then those were like the first limitations found for computers, theoretically. And then Bryce's theorem further shows and states that any non-trivial and semantic property of a program's behavior is also undecidable, which has major consequences in software verification and AI reliability. Some examples of these undecidable properties would be, does the machine accept any string? Is the language empty or is the language regular? So those are all undecidable. And then with Rice's theorem, it's just all about determining which properties of languages are recognized by Turing machines, which are undecidable. So AI systems like neural networks are often seen as intelligent, but we can't fully understand or predict their decisions in every situation. The limits exposed by theoretical computation mean there are no guarantees that an AI will always have or always behave safely or interpret data correctly. This challenges our ability to create truly explainable or trustworthy AI. So some of those limitations on computers also reflect on AI as well. And then this goes for machine learning as well. So in machine learning, we face the issue of never being able to find the best model for all problems. The no free lunch theorem tells us that no one algorithm works best across all data types. Combined with overfitting and algorithmic unpredictability, we realize there are fundamental limits to what machine learning can achieve, even with more data or better computing power. So then, interestingly, undecidability isn't just a machine issue, it also reflects limits in human reasoning as well. We program machines based on our own understanding. So if a problem is unsolvable for a computer, it may also be beyond human comprehension. This mirrors our own logic and cognition, or wait, sorry, and cognition are subject to constraints like Gödel's incompleteness theorem, which this theorem took me a long time to understand. So I linked a video here just for like, if you want to understand a better grasp of it, which I'm not going to play for time's sake, but yeah, he explains it really well and like does like a whole like little math equation. And he was like, yeah, maybe us humans can maybe understand this theorem. It was super hard to understand though. And then as for case studies and real world examples of these limitations, we could see these theoretical limits in real world examples. Self-driving cars can't be formally verified to behave perfectly in every scenario. Chatbots may hallucinate facts because they're guessing based on incomplete knowledge, and AI alignment, ensuring that AI systems do what we want, is still an unsolved challenge, as seen in ongoing efforts by OpenAI and DeepMind. And then to wrap up, Theoretical limits like the halting problem and undecidability show us that not everything is computable. These limits are crucial for understanding the risks and challenges of AI development. So going forward, it's vital that we develop AI systems with humility, caution, and a respect for boundaries of computation. And then those are my references.
So, questions? We should have someone else ask.
Haku.
So, so this is just a question that I had when you were talking, just get your opinion since you went on this.
Yeah.
Research. So, see that there are limitations that have been seen in programming in computing. My question is, are those limitations because people are the ones who make this algorithm?
Yeah. Exactly.
So are these limitations? Are not these limitations because of the people who make them? Aren't them because we who make the algorithm are not, go beyond the certain limit. And because of that, algorithms we also gonna make, they're gonna be limited. Because we are also.
Yeah.
Oh, yeah, that's just my thing.
Yeah, I know what you mean. Yeah. I wouldn't say the limitations are because of us, but like I would say like kind of what you said, like there's limits to what we can solve.
Yeah.
So like obviously when we program like an algorithm or try to come up with a solution for a problem, we can't code or create something that we don't know yet. So like
Yeah.
we can try to come up with a solution, but there's even limitations to our reasoning
Yeah.
to like, okay, what is the shortest path to get to this one location, right? And if we don't know, how are we going to code that? It's like how, yeah. So it's like just a reflection of our own thing too.
But why some people like studying math or this theoretical stuff, but kind of trying to answer questions beyond what we can do, try to say, that, math guys say, the universe, given this logical system, you can't do this. Some people find that very, very comforting. But then you get into like the incompleteness theorem and then your comfort kind of disappears.
No, a lot of the theorems dealt with like mathematical equations and like if L stands for this problem and then this done, I had to like watch so many videos and had chat explain to me. I'm like, so is this what it's basically saying? Like with I kept confusing Rice's theorem with incompleteness theorem too as well, because like one was proving like when a problem is undecidable and like I got a little confused there, but then like it made sense after watching the videos.
And Google's, like you're saying that are undecided. What ones? Yeah, that one is also very hard. Like you were saying that video.
Yeah.
I was going to ask you what you found most challenging, but I think you just described it. It's just keeping track of all these different, very closely related mathematical concepts.
I was going to ask you, so you say they are certain problems that have been deemed and they never going to be solved, unsolvable. Do you think that in the future those problems are going to be solvable? Because why? Because in chemistry, when I was doing chemistry in high school, we would be told, all the rules that, this chemical doesn't react with this chemical, or this type of elements don't react with this type of element. And then after that introduction, we told, oh, but there's a discrepancy. Within those elements, there's a certain one that can actually, or that does not actually follow the rules and all that. And in that process, it just made us understand that in the first place, they thought, that all these elements are not going to be able to do it. But as time went on, they discovered that no, actually some elements we can do it. So I just want to ask you if you think that, if it's an unsolvable, it's never going to be solvable, or it's actually, there's a possibility that in the future, you might find an algorithm that
so like I think with some of them, I think that they could, but it would just take a lot of research and dedication, like maybe one's entire life. Kind of like I feel like how they did with like chemistry and all that. Like it was just a bunch of research and like in the lab. But with some of them, I don't think they would be unsolvable. Like I kind of want to quickly just show like this video, like how he explains it, and like it kind of was like, okay, yeah, like how would you solve that? Like he was like, sometimes an algorithm can't even prove its own, like if it's true or not. Like I don't know how to explain that. Uh, is the volume
That's the wrong.
or is it this? Oh, yeah.
That it's just thorough and complete there. Some people have heard of perfect Google. They know it's important because the first time
Kind of sounding good
out
to know.
with during the
That's
Princeton,
good.
Okay.
uh,
Um,
they have perfect completeness there and its relation to.
I just want to skip to the part where he's like talking about it.
This is the most sophisticated advanced imaginable. I looked at UTM for universal truth. They any truth in the universe. And that's because it's so ultimately intelligent and advanced. Because I knew that universal truth checked out. Whatever. So what he wants to do is he's going to back this machine into a car. And I'll show you how he does this. He writes out set. UTM will never say G is true. But here's the self-referencing part. Let's go slow with this. He actually reads a reference to the statement. The statement itself is UTM will never say G is true. Then he calls that statement G. But here in all my technical communication, we should kind of ponder that for a little bit. So G is the statement. UTM will never say G is true. Now he writes this out just like I did to you. And then he shows UTM the statement and asks UTM, is G true or not? And here's the cool part, and it hasn't hit you yet. So again, I could be staring at this. Imagine giving this UTM back to UTM is the most metaphysical cosmic point possible. If UTM says G is true, it makes it false. So the UTM machine is supposed to be capable of saying any truth possible, and not saying what is actually true, and in doing so, makes it actually true. Okay. And you have to pause.
Yeah, so I don't know if that made sense, but like you basically made G equal to UTM will never say is true, even though it did say that it's true because it's equal to that. So
You see in a lot of these things, even when you get the undecidability, it's almost always given any machine, and you can always then construct some machine that's gonna break that, for every possibility, where if you have just one thing, one example, if a human can program one example, then you can look at it, but
yeah,
we're trying to make these very general statements.
yeah.
That's, thank you.
Yep.
How are we doing? We are right on time. Ready to go, Addison? Tell us all about Rust.
My name's Adson. I'm going to talk about the Rust language and its systems. So Rust is a general purpose coding language that is statically typed and it's specialized for memory safety. Uh, Essentially what was going on was most of the coding languages that companies were using, they're finding there's a lot of memory safety vulnerabilities. So Rust specifically was designed to combat some of these issues. So just to talk about memory safety a bit, even today or kind of recently, and there's a study in like 2019 where 71.5% of all vulnerabilities in Mac OS was from memory safety. And also 66.3% of all vulnerabilities in iOS 12 software were also memory unsafe. So memory safety still like persists as something that is important, and like companies want to try to figure out how to prevent like data loss or infiltration and stuff like that. So some of the key features about Rust is they have a thing called zero cost abstraction. This basically means that you can use generic values without having to use generics. Uh, they also have pattern matching, which will basically automatically match your values. So there's no like potential data races or anything like that. And then the main feature that makes Rust unique is their ownership and borrowing systems. So for ownership, it has like these set of rules. It's each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. So to describe this, let's say there's a value A and a value B, and value A is equal to 1. So in memory, it will say that, value A is pointing to 1, but value B is pointing to B. If that was in like Java, you'd have 2 pointers for A to B and A to 1. But in Rust, instead, A will lose its ownership of value 1, and B will assume ownership of that. So this just ensures that you prevent like data races and undefined behaviors. And then the borrowing system, it basically guarantees that references will always have a point of, they'll always point to valid objects. So you have to use like this and symbol to create a copy of the value, and then that copy will have all the mutability of that value, but it will not be like a new separate value, basically. So where is Rust used? Some of the big companies that's used in, it's used in AWS, which is Amazon, Google, Huawei, which is a Chinese company, Meta, and Microsoft. Amazon uses it for some of their infrastructures, and they're also like using it to update some of their CloudFront and like Amazon services. Google uses it mostly for Android and some Linux kernel like systems. Huawei, they're actually reworking their whole code base from like C and like C++ to Rust because they think that's going to help with their memory safety issues. Meta uses it for AR and VR, which is important because you don't want like if you're in AR or VR, if you're using it, you don't want to like lose track of where you are or anything like that. And then Microsoft uses it currently to update some of their Windows libraries. So in conclusion, Rust is a pretty strong coding language. It has a lot of features, but it is also in that kind of extreme territory where it is very memory safe, but how safe do you really need to be? But it's a good language, and it's becoming a core language in businesses and companies around the world. And that's about it.
I wanted to ask why you decided to choose Rust just out of curiosity, because I think that I had a few bullet points on Rust as well.
Yeah, so well, when it was in the final project, like topics, So that was one of the things. But I also was hearing a lot about Rust. I was hearing like just some companies that are using it. It's kind of like becoming a popular language. So I just wanted to research more into it.
Is the syntax similar to C or C++?
Yeah.
I mean, it's often used as a replacement for C or C++.
Yeah, so it has like similar syntax. You see like the FN
Yeah.
and like since it's statically typed, you don't type the variables, you just go like let stuff like that. So it is pretty similar to C++. I think it was modeled after C++.
Do you think there's any idea that maybe the designers of Rust would, release future kind of updates to kind of tone down just how extreme they are with like the memory safety?
I think that's what makes Rust kind of unique though. It is like very memory safe. So I don't think they should like tone it down, but they should update to like make improvements or potentially just make it easier to code. Because like Rust is kind of a hard language to learn. It has a high learning curve. So
Yeah.
for like especially new users, they're not going to maybe understand like how their compiler works because the compiler I never mentioned this, but the compiler uses something called a borrow checker, and that's what enforces all of the rules for the ownership and the borrowing and that stuff. So if you don't get the values, the ownership of the values correct, it will just not compile. So that could just be difficult.
Yeah.
Okay. Somebody ready to go?
Okay, so I did my final on understanding asynchronous programming. It was like a cross-language tutorial between Python and JavaScript. So let me just dive into it. So what is asynchronous programming? This allows performing tasks without blocking execution. It's a programming method that allows a program to initiate a task and continue executing other operations without waiting for the tasks to complete. It is commonly used for to improve efficiency and responsiveness, especially in applications that perform input-output bound tasks like reading from files, querying databases, or making web requests. It is essential for apps and concurrent processing. It's common in web servers, databases, and real-time user interfaces. So like a real.
My old eyes can't read.
Okay.
That well.
I have some talking notes also.
Oh,
So
does that show the documents?
I don't think it shows on the slide.
Yes, well, that's fine. Go back there. Okay.
Yeah. So yeah. So like a real life example to make this easier to explain, synchronous programming would be like maybe you order food and you just wait silently until it's ready. But with asynchronous, you order food and then you're able to like check your emails, talk to someone, do some activities while you wait for the food to be complete. So it's more like asynchronous makes you do other things at the same time. You're waiting for the task to complete. But with synchronous, you can only do like one line at a time, which is different. So what are the benefits of asynchronous programming? There's improved responsiveness, there's better resource usage, and it scales under high load. But it also has challenges. There's code complexity and it's harder error handling and debugging. So Python uses the async. So async defines a coroutine and then await process execution until result is ready. And then async.run starts the event loop, which is commonly used for input-output bound tasks, as explained. I have this YouTube video, which is a short 2-minute video to explain what happens.
Using traffic to my competitors? Good thing I have severance. Now I know who's outrated.
Async await. Oh no, is this going somewhere off of Python? Well, it's not. We can use async await in Python too. Let's see how. Consider this function. The task is an asynchronous function because it's marked with the async keyword. In Python, when we mark a function with the async, it becomes a coroutine. Coroutines can be paused and resumed, allowing other tasks to run in the meantime. To use async await in Python, we need to use the async IO library. So what's the need to write asynchronous functions in Python? By using async and await, we can write non-blocking code that performs tasks concurrently, resulting in faster and more responsive programs. Here we have two scenarios. On the left, we have a synchronous function, and on the right, we have an asynchronous function. Both functions do the same thing, and we are checking who's going to take less time to complete over 10 laps. Here's the output, and it clearly shows that the asynchronous function won by a big margin. That was fast. Asynchronous functions don't wait for one task to complete. They go all in executing tasks concurrently. Let's see another one. Here we have two functions, load_data and task. The load_data function simulates loading heavy data, while the task function simulates a normal task. The main function executes both functions in sequence concurrently. Upon running the code, this output is generated. This shows that while the program begins loading the data, another task gets executed in the meantime, and the program exits once the data is completely loaded. To recap, async and await are essential tools for asynchronous programming in Python. By marking functions as async and using the await keyword, we can write non-blocking code that performs tasks concurrently, resulting in faster and more responsive programs. Thanks for watching. Don't forget to like, share, and subscribe for more Python tutorials.
Yeah, so that was an informative presentation, like just video overview of how asynchronous programming works in Python. So this is just an example from the video. Here is a simple Python example. The fetch.data sleeps asynchronously for 2 seconds and then continues. This lets the program remain responsive during that wait. And then also in JavaScript, we started with callbacks, then moved to promises, and now we use async /await. Asynchronous functions automatically return promise and await process execution until they resolve. So this is just like in comparison with JavaScript, the syntax, and then the JavaScript example code. So in JavaScript, the example shows a delay using a promise. The fetch data function waits for 2 seconds and then continues. It's very similar to the structure in the Python's example. So comparison, just getting further, Python requires an explicit event loop using async, while JavaScript event is built into the environment. Python uses coroutines. JavaScript uses an event-driven model. Both languages share the async or await style today. So running tasks in parallel. Both Python and JavaScript allow running multiple tasks at once. Async.gather in Python and promise.o in JavaScript. This approach reduces data wait time and improves efficiency. Those are the syntax that you use in Python or JavaScript in running asynchronous tasks in parallel. And then reward applications, as mentioned at the start, it's used in web APIs, it's used in database access, user interfaces, and streaming. For example, when you're using like Spotify, Netflix, you can be able to play music and kind of like, do other things at the same time, which is asynchronous programming. So conclusion, asynchronous programming boosts up responsiveness. It's crucial for scalable modern systems. And it's learning across Python and JavaScript to broaden the developer skill set. So, and then these are my references. Yes.
Cool. It's actually interesting to as you mentioned that you can be able to listen to music while also doing something else and playing video. And it seems like asynchronous programming is now pretty much everything that you do. But my question is are there scenarios where synchronous programming preferred over asynchronous?
Yes, I think there are definitely cases where synchronous programming would be preferred. But I think nowadays is more less than that because nowadays things are moving fast and people prefer apps that are able to multitask at the same time. But I'm not sure of a good example to give you. But I'm pretty sure there are specific instances where synchronous programming is needed. But for most tasks nowadays, I think asynchronous programming is the preferred option since people are used to multitasking. So
Done much, have you used these in projects or real world at all?
I haven't used it in a real project, no. But I've just been learning about it. So
I don't know if you've done full stack, if you use it in full stack. That's why I'm using it currently is in a JavaScript, web page. Because again, nowadays, a web page is actually multiple. But you'll have one script updating one part of the script, one part of the page, and then you may be waiting to display something else on another part of the page.
Yeah.
So you'll be running, a couple AC, not to get you're waiting for a data to update or back end updates like coming in. So I don't know if you can get there.
no, we are doing full stack next fall. So we haven't done much of it. But yeah, I think that would be a good case where we use asynchronous. So
Thank you. I'm gonna try one more thing. I'm curious because we did this. Because this is mirroring the screens. I just wanted to see if we don't mirror them but extend them. Oops. Okay. And because with PowerPoint, if you have dual monitors, right, and you hit present, it'll present on one monitor and your talking points. Yeah. So I was just curious because he had it talking points because I never tried it in this, So okay, so it doesn't actually seem to work in Google Slides. Interesting.
That's pretty interesting. Yeah.
Yeah. Okay.
I was gonna say that's definitely something I remember PowerPoint.
Yeah. Right. Okay. You can open up your.
Sounds good. Yeah, so I did mine on generics, and when I was looking at the class upload, I saw that Grace already did one on generics. So if you saw that, you're gonna get to learn a little bit more about generics. And this one I will say I did do an example. I did a little bit in Rust just to kind of showcase something. So that's maybe something different. I don't know a whole ton. I definitely don't know as much as Addison about Rust, but I just wrote a little bit about it just to try and showcase a different usage of generics. So yeah, just in general, generics allow for creation of code templates, irregardless of the data types being used, which is great for reusability. I mean, that's the key. That's kind of where generics are going to get the most usage out of is, big enterprise code development when you need to be able to write code that is be able to, be reused regardless of the type, A, and secondly, it's extremely clear when you write a method because you're putting it within directly within brackets if it's an integer, if it's a string, and it kind of removes the need to cast to integer. So it's simple in that sense, reusable. Definitely been getting a lot more usage ever since Java added it in one of their updates. But I mean, it's something that generics I think are only going to be more and more widespread. So here's a little example in Java, and what I mean within not needing to explicitly cast it is that within the hash map, if you look where it's listing integer and string, it's immediately clear that this is what the two returns are going to be. And it also allows within one hash map to have both an integer and a string. You're defining it as a key and a map key set. So at the very end, it's going to return one, an apple, or two, and a banana. But it's mostly just useful for the reusability of this. And once you have these type of methods written, it's very simple to change. If you want this to be an integer and an integer, it's really, you're only changing one word here as opposed to an explicit cast within it and a whole nother line. And while it might not seem like a big deal, it honestly would. It adds a lot of time if you're working within, hundreds of code classes for enterprise development, and you need it to just be as simple as this. So this is kind of a generic, a Java example. This is an example in Rust. And, once again, I don't claim to be an expert in Rust. I just wanted to showcase a different way that they do it. But you can see they have the same idea with explicitly showing the T and the U and then providing, an X and a Y. And this is an example in which they're implementing a mix-up function so that it's allowing for different returns at the X and the Y part. You're still using the T and the U as the returns, specifying it. But I just wanted to showcase a different example in Rust. And the other interesting thing with Rust, this has to do with how strict they are with type safety. Rust generics actually run almost double, if not like triple the length at compile time because they create a version, let's say it's T and a U, instead of Java, which checks at compile time if things are correct. If let's say you feed it into a string, Java will check that at compile. Rust would actually create an entire version of the code for an integer and an entire version of a code for a string, which is going to almost double the compile time. And that's kind of where that's where you could argue it's definitely overkill on the type safety, but that's also why you end up using Rust is for that robust type safety, whereas Java would just throw an error when it gets to compile time and realizes, oh, you put in a number 2 instead of a word. Rust would have already had all that planned out. So, definitely a trade-off and definitely a use case of that. Another application of generics I just want to showcase in Java. This is another one where you're explicitly defining it's going to be a string, but you don't have to use a separate line to cast it. You can just put in string there, and it would be just as easy to change it to an integer. And it's also not going to throw any errors. Like let's say you put in a number, let's say you put in 5 right here. It's instead of running into an error like you normally would if you said there was a string maybe name. If it's just an integer in this scenario, it just wouldn't print it out, but you also wouldn't have an error. So that's a positive in terms of type safety. And when you get to compiling, especially big projects, you can't have errors just because someone puts in an integer and they forget to change it. So that's one area where generics just have a lot of use. And then just some final thoughts on it. I just think generics have become a lot more popular, and they're also extremely useful in terms of reusable design. And the safe code execution is an important part when you look at usage in Java, Python, C#. Almost every coding language is going to use generics, and there's a lot of work that I think generics will be able to accomplish in the coming years too, once people have more written about them. And they really are kind of becoming the skeleton for modern code in the sense that a lot of boilerplate classes and, methods are going to become just being, generics are going to be used within those boilerplate code scenarios. And I think that it's something that you're going to see a lot more behind the scenes in modern development. You look at the best, software development areas, companies, I think they're going to keep using generics.
Generics getting popular. I grew up in the era of object-oriented those, that, or, so you'd have an employee class above some of those and a person class above those.
Yeah.
And then you could, write a script that would take a person and it would handle any of those things. And like in game design, you also like Unity they have an object type and then almost everything is built off of object type, inherited from object type.
Yeah.
So is your thought that, we don't need this sort of inheritance so much? Because again, it seems like generics is kind of handling some of, letting us do some of that.
Yeah, there's definitely something to be said about that. I mean, I think a lot of it just depends on kind of the usage. I mean, I do think there's a large place for inheritance. And once again, I feel like, just how much Java coding I've done throughout my time here, I think that's something like object-oriented programming is definitely the way I'm used to it. So getting used to generics was really foreign because there's a lot of ideas within it that are kind of opposite of a lot of the stuff that Java's, working on with the key like inheritance and object-oriented stuff. So I do think there's probably more. I think inheritance and that kind of those kind of idea of writing code in that sense will probably be less and less popular as generics get used more and more. But I mean, there's definitely room for both. I think that's probably the middle ground you're going to get with it.
What did you find for good sources? I keep forgetting to ask people that, it's always challenging, I think, for me to find, there's so many, like, you look up generics and there's, so many sources out there and so many websites, so many videos and stuff. So
yeah,
what did you find as far as good sources?
I did really enjoy the Java docs themselves were actually, pretty informative on this. It was interesting to read about like type erasure and all the work that Java does. And also the other area I really enjoyed, the Rust documentation was really well done as well. So I feel like that was one scenario I just went almost like straight to the source of the language for the documentation. And
that is surprisingly good a lot of times, but a lot of
yeah,
I don't do that.
It was good. I mean, and also I just even for when I was writing it, trying to get a little bit about Rust just to get a different like application in generics. I mean, I know nothing about Rust. So and that was one where I was like, how am I going to get good sources and be able to write about this effectively? So I definitely had to go right to the source docs and try and learn a little bit about how Rust handles generics. And I just wanted to get a different look at, the way that Java handles generics is a little more carefree, I guess. But whereas Rust is so, demanding with the returns, and that's kind of where I wanted to get some good documentation on Rust in particular, because they really do interesting handling of generics.
Yeah, I can see a lot of content creators will create videos like, oh, that's a really good example. And then later on, I'll be looking at the actual documentation and go, oh, that is the example of the documentation.
Yeah.
You just gave me the example. Or else you'll see, and you start seeing, the 4 different content creators all using the same example. I got to go, where's the
source?
Where is it example? And often from some sort of original or a good article. And
yeah.
For borrowing.
Yeah.
All right. Any other questions? All right. Good job.
Thanks.
Are we waiting for Heba here? When she's scheduled up? Yeah.
Is Eva coming there? You heard from her? Yeah, she was. Okay.
She's coming. She's got a minute. You got 60 seconds. You don't even have to run. You're good. You're plenty of time. No hurry at all. We weren't worried at all. Sit down, relax. Jeffrey, why don't we have you go and let Eva catch her breath. We want to hear about Ruby. If Jeffrey was here early, he's been here the whole time. Obviously.
So the topic of my research paper was on Ruby and basically just the language itself. So what is Ruby? It's a high-level dynamic programming language. It's known for its elegant syntax and strong emphasis on simplicity and productivity. The objective of its development was to make it act as a sensible buffer between human programmers and the underlying computing machinery. And it has approachable syntax, but is a highly expressive and flexible language that offers advanced features that allow developers to write powerful abstractions with minimal code. So some of the history and the philosophy behind Ruby is that it's created by a Japanese computer programmer, Yukihiro Matsumoto, and he wanted to create a language that favored intuitive code and human-friendly design over machine optimization. Republic released this in 1995, and he goes, one of his famous quotes is that Ruby is designed to make programmers happy. It was created with the human-first philosophy. One of its defining goals is to prioritize developer productivity by allowing natural and concise code expression. And he believed that code should read like English and reflect the programmer's intent clearly. And that can be seen in Ruby's syntax, which avoids unnecessary punctuation and favors convention over configuration. Some languages that Ruby took inspiration from. It draws inspiration from several different programming languages that each contribute to a unique aspect of its strength. From Perl, it took its text processing capabilities and scripting flexibility. From the language Smalltalk, it took its pure object-oriented principles. And this is where every value is an object and operations are implemented as method calls. From Lisp, it took support for closures and dynamic evaluation. And then from the languages Ada and Eiffel, it took its emphasis on readability, safety, and modularity. Some of the core syntax and language paradigms of Ruby is that it's a dynamically typed interpreted language known for its clean syntax and powerful object-oriented features. Features automatic garbage collection, pure object-oriented in nature, so everything is an object, including primitive data types such as integers, booleans, and even nil, which is Ruby's equivalent of null. And because of Ruby's uniform object models, developers can make method calls directly on numbers or nil. So an example of that would be this line of code, which is it's making a method call directly on the integer 5. So this just prints hello world 5 times around the console. Another part of its core syntax are blocks, which are anonymous chunks of code that can be passed to methods and executed. These enable elegant iteration and functional style programming without the verbosity seen in languages like Java. It's a chunk of code that you pass to a method to be executed. So in this snippet of code here, the block is do num puts and then the number multiplied by 2. And it's really good at going through collections. So it'll print each number in that collection multiplied by 2. And as you can see, it avoids unnecessary punctuation and favors readability. And the variable declarations are implicit, so there's no need to specify type for the variable either. And you can see that semicolons are rarely used in this language. Some of the advanced features of Ruby are metaprogramming, open classes and monkey patching, mixins via modules, and reflection. For metaprogramming, this is a programming technique that gives computer programs the ability to treat other programs as their data. So that means that a program can be designed to read, generate, analyze, or transform other programs and modify itself even while running. It's often used to write more efficient, flexible, and adaptable code. And in Ruby, it can be used to dynamically define methods and classes, modify existing classes and methods, and inspect and manipulate code objects, which can help drive code and help developers write usable code or create a library that can be extracted as a gem, which is just an open source library in Ruby. And then some metaprogramming methods include send and define method. So for the send method, as you can see before metaprogramming, you'd have a bunch of if and else if clauses, but you can replace that with the send method, which will the send method will take 2 arguments, those being the name of the method to call and any arguments that should be passed to the method. And the name of the method can be passed as a string or a symbol. So in the updated code that uses the send method, a couple of things are happening. The respond to action checks whether the order shipment object has a method with the name passed in the action. And this is a safeguard to avoid calling methods that don't exist. Order shipment.send action. That is the key metaprogramming feature here, as it dynamically calls a method by using the string or symbol stored in action. So if action is dispatched, then Ruby would call order shipment dispatch instead of using the long if-else statement. So when you leverage Ruby's reprogramming metability, dynamically dispatch the message at runtime. The define method. So in the define method function, it can be used to programmatically create methods. So if we want to check the order shipment status, we might implement the method as follows in the order shipment model. So instead of using the repetitive code that can be seen in the first code block, you can use the metaprogramming function define method to create all the functions dynamically. So here it will create the method for all the status values defined in statuses, and then the methods will be the same name. It'll be is initiated or is dispatched and need to be called in the order shipment object. For open classes and monkey patching, these in Ruby classes are open, meaning they can be reopened and modified at any time, even core classes. This allows developers to extend or alter behavior globally, a concept known as monkey patching. And then monkey patching in Ruby is a technique that allows you to modify the behavior of existing classes and modules at runtime and can be done by reopening the class or module and adding or overriding methods. So in this example of monkey patching, the string's reverse method is overridden. So the new reverse method splits the string into characters, reverses the order of the characters, and then joins the characters back into a string. While monkey patching can be a powerful technique, it's also a controversial technique, although it allows for elegant customization, it can introduce conflicts in large code bases or dependencies if it's not managed carefully. So this is why when using monkey patching, developers will often use refinements or explicit modules to limit the scope of these changes. Mix-ins via modules. These avoid, because Ruby avoids traditional multiple inheritance in favor of mix-ins, which are implemented via modules. In a module, it can be mixed into a class using include for instance methods or extend for a class method. So in this example, a module named greeter is defined, and then a module in Ruby is like a container for methods, constants, and other modules or class definitions. So the greeter module contains the instance method greet. And it's important to note that these modules cannot be instantiated on their own, as they are instead meant to be mixed into classes. So by writing include greeter, we are mixing the greeter module into the user class so that all instance methods from greeter become available in instance methods in user. Mix-ins in Ruby are used instead of inheritance because Ruby does not support multiple inheritance. So this would be reflection. So Ruby supports reflection, which allows a programmer to examine and manipulate its own structure and state. So this includes querying classes, methods, and variables at runtime. So the bottom two lines in this are where you really see how reflection works in Ruby, as it'll take a symbol or string representing the name of an instance variable and return the current value of that variable, even if it is private or not directly exposed. So even though there's no public method, you're able to access the value dynamically. So practical applications in the ecosystem Ruby. It's most famously associated with web framework Ruby on Rails, but its utility extends well beyond that domain, and Rails remains one of the most popular ways to build full stack web applications. A major area Ruby excels in is scripting and automation, because concise syntax, dynamic typing, and reflective capabilities make it a natural fit for writing automation scripts and small utilities. It also has a very active community that create a bunch of open source libraries known as gems, which can be easily managed and installed. So this ecosystem greatly extends language capabilities, allowing developers to add functionalities like authentication, data validation, HTTP requests, or background jobs with minimal overhead. And some tech companies that use Ruby, GitHub had originally built itself on Ruby on Rails. Shopify still relies heavily on Ruby today and invests in its performance and scalability. And Basecamp, which is the product management tool, was actually created by the team behind Ruby on Rails and continues to use Ruby extensively today. These are my references.
Have you used Ruby on Rails? Again, that's the only place I've ever seen Ruby is with Ruby on Rails. I never really used it that much. So.
I haven't used it.
Do you know of any like big websites or any like are there any usages of Ruby or Ruby on Rails that you found that were like, you know, I don't know, like Twitter or something, or anything?
I think one of them I found, Netflix, uses some Ruby every once in a while. So that's a big company that will use Ruby.
Nice.
Other questions? What was most surprising to you when you were doing this Ruby, you know, compared to other languages? What did you find most different?
I'd say the syntax was very, like, no punctuation hardly anywhere, and like no semicolons or anything, just indentation pretty much.
Right. Yeah. Yeah, it seems to be, but when I tried to read it, it's hard. All right, good job. Anybody ready? All right.
So, have you ever wondered how they used to program these military aircrafts during the Cold War? Well, that's when Jovial comes in. So, Jovial is short for Joule's own version of the International Algorithmic Language developed in 1959. Jovial was designed specifically for military and aerospace systems. It played a crucial role in powering mission-critical operations, including US and NATO, which stands for North Atlantic Treaty Organization Air Defense, radar tracking and airborne control systems like AWACS, which stands for Airborne Warning and Control Systems. Although it is rarely mentioned in today's classroom, Jovial was once a cornerstone of military software development, offering programmers deep control over hardware, something essential for high-stakes real-time computing in defense systems. During the 1960s, Jovial was part of the U.S. military ALP project series, particularly the ITT-4605L Strategic Air Command Control System, which is the Strategic Automated Command and Control System project. It was also a Cold War Big L network of computer and communication systems for command and control of strategic air command, combat aircraft, refueling tankers, and ballistic missiles, due to a lack of real-time computing programming languages available. Okay, so Jovial was created by a team at Systems Development Corporation, which was a computer software company based in Santa Monica, California, and began as the systems engineering group for the SAGE, which stands for Semi-Automatic Ground Environment Air Defense Systems at the RAND, Research and Development Corporation. This was headed by Jules Schwartz in 1959, and the primary motivation for the development of Jovial was to create a high-order programming language for composing software related to the electronics of military aircraft. Fun fact, while doing my research, I found out that the 552 Airborne Warning and Control Wing, which is basically just an operational wing of the Air Force, relied heavily on this programming language, as well as the digital heart of the AWAC, which I already explained, stands for Airborne Warning and Control System. Okay, so the creation of Jovial was shaped by four major developments: the SAGE program, Project CLIP, the publication of ALGOL, and the SACSS program. So SAGE was launched in the 1950s and was a massive Cold War air defense system that demanded real-time computing and reliable software. CLIP, which stands for Compiler Language for Information Processing, introduced foundational ideas in compiler design, like expression parsing that directly influenced Jovial structure. The introduction of the ALGOL programming in 1950 further shaped Jovial syntax and semantics, inspiring its shift towards structured high-level programming suited for complex systems. Finally, Strategic Air Command Control System required the language robust enough for mission-critical defense application, so defying the need for Jovial's development. Okay, so some capabilities of this language and its syntax are strong typing and detailed data descriptors, segmented memory management. So it's a way for computers to organize and access memory rather than dividing it into different sections. And these are examples of the syntax of Jovial. Fun facts, I actually couldn't find like a real code like when they used to use it back in like the Cold War because of security reasons, I guess, like safety reasons. So this was just an example that I was able to generate through AI that it said that like it could be an example of how they used to do their defense system or triggering system for like their machines. So pretty simple, just a if statement and else and if. And for my conclusion, Jovial's continued presence in military infrastructure underscores its lasting impact on defense technologies. While it's originated during the Cold War to meet the demands of real-time, high-reliability systems, its legacy lives on in the maintenance of critical aerospace and military equipment today. For students interested in fields like cybersecurity, aerospace, or defense systems, even a basic understanding of Jovial offers valuable insights into how legacy code still supports modern operations. This highlights the importance of including historical programming languages like Jovial in computer science education, not only to preserve the past, but to prepare future engineers to maintain and understand the systems still shaping national security. And yeah, pretty much it. Any questions?
You come across this?
Yeah, so I actually just like Googled random, like what are some programming languages that are not taught in classes? and are still used even though like even if they're old. And I came across like this article by this random person who used to work in the Air Force and said that he used to use it a lot in the our like running system or something like that. And I just thought it was like pretty cool how like there's literally specific languages for military purposes and they used to use it during the Cold War. So yeah.
Yeah, I mean, it's still the same age as like COBOL or Algol.
Yeah, Algol.
You know,
Yeah.
and it's surprising how much COBOL is still out because
Mhm.
I swear every 3 years we get someone coming to us and saying, you know, you should really teach a course in COBOL, and we can do that. And I'm like, we're not gonna.
Yeah.
You can't find, you know, because you have to hire 2 people in the next 5 years to use it. That's not, no. We
Mhm.
can't teach a class with those 2 people.
Yeah.
But it's surprising how much COBOL, you know, like you look at places like Securian there, and you know, they're still running on a mainframe system. A lot of their core stuff is still running on an old mainframe system, and it's still a lot of the under the stuff. A lot of it is still COBOL, and then they put libraries, they put web, and they put Java stuff on top of it to access it. But the part of it is still there. So I would guess, you know, there's still a lot of jovial out there.
Yeah. Mhm. Yeah, they use it a lot in the like military systems and like even to update those old systems, they obviously need to use it because like the syntax isn't jovial. And I think in like I remember like watching this old movie about like I think it was called Blog Hawk something and like they used jovial to program that helicopter for that movie. So that was pretty cool.
Yeah.
Yeah.
Yeah, a lot of those languages, like the military has certain requirements of their languages.
Yeah.
And they often have, because again, they're kind of mission critical and stuff like that. So, they often require, you know, that you write code and then you prove or somehow demonstrate, you know, where we might write a couple of unit tests, they often have some sort of a, you know, a system that goes through and proves that it's working or something, you know, some sort of verification process on each one, you know, each section of code. And so, once you get that kind of set up, you know, with these or certain languages. So I always think, you know, Jovial and like Ada is the other one that's used a lot in the military because of the structure and how it's been reviewed and, you know, allowed in the military. Where you can't just pick up Python. Insecurity problem. What kind of resources did you?
Yeah, so for my resources, I used the manual of Jovial, and then I like relied heavily on this research paper that I found. It's called The History of Jovial Study Programming Language Change, and it was a master's thesis from California State University. So it had like the 4 major basically like reasons why it was created. So I took like most of my resources from that paper and also the manual for Jovial.
I find master's thesis is really helpful.
Yeah.
Doing research sometimes you can find someone who's, because my experience is that if you find a PhD thesis, it is just too big and too complicated to help. But if you find a master's thesis,
True.
it is again focused on a whole topic and explains the whole background and stuff. So I really like to find a master's.
Yeah, definitely helped a lot. Yeah.
All right. Yeah.
Thank you.
All right. Did we get to everyone today? Just a couple then quick announcements. We'll see some of you at graduation there. I sent out some new jobs if you're still looking for a job or something like that, or an internship. I'll probably do one more later on. And again, sometimes we hear stuff in May, so watch your email there. We're looking to send students to a diversity conference next fall. And so we did Grace Hopper this past year. So we're doing Afrotech, which we haven't sent a group of students to before. But we're now, did you attend Afrotech? Either of you? No, you just heard. Okay. Because I know I thought you went to another one, but I thought that was a winter one. So we're gonna try that one out. And again, you can apply for funding there. We have limited funding. So like with Grace Hopper, I think we had 13 people apply and we had funding for 4 people and we scrounged it and did 5 there. So we can see how that, what we can have. Also in that link, I put there's a lot of other conferences we can go to. So I just wanted to highlight all the different conferences you can kind of plan to go. And I'll send out an email. I don't know if anyone is going to the Data Tech conference that's coming up in a couple of weeks down in Minneapolis. And if we need rides, so I'll check for an email if anyone. It's sold out now, but if anyone got in and is going to that one. So, all right. Otherwise, have a good summer.